Hey everyone, sort of. Recently I published a video about the tunnel diode. In my opinion, it was one of the most interesting videos on the channel and a lot of people appreciated it. I highly recommend you check it out. Trust me, you won't regret it. So in that video, I promised that similar videos would be coming out in the future as well. And today we've got another interesting video about yet another mysterious electronic component. I'd like to ask you to share this video, rate it, and leave a comment. This is invaluable support for the channel and will help make more videos like this possible in the future. From the last video, we know that semiconductor diodes come in all sorts of varieties: classic diodes, LEDs, photodiodes, laser diodes, and many others. But they all have one thing in common. If we're talking about semiconductor devices, almost all of them have a p-n junction, all except at least two: the Schottky diode, which has a junction but of a different type, and the Gunn diode. And it's the latter that I'm going to talk about today. Most likely, many of you are hearing about this diode for the first time, and that's perfectly normal. These aren't common components, at least not in household devices. This diode is so unusual that it only has N-type crystals. That's right, it doesn't have a p region. It also doesn't have any barriers. It doesn't rectify anything and doesn't have one-way conductivity like a regular diode. It was created for one purpose: to generate ultra-high frequency oscillations. And sometimes at such high frequencies that even many modern microwave devices would envy it. A Gunn diode made from gallium arsenide can generate oscillations at frequencies up to hundreds of gigahertz. With other materials, the frequency can reach up to 3 terahertz. Transistors from that era couldn't even come close to operating at such frequencies. But what was the purpose of such a diode? The 1960s were remembered for many events. In terms of technological development, especially in the electronics industry, the world was just beginning to move away from bulky and power-hungry vacuum tubes in favor of compact semiconductor devices. Of course, there were fairly high-frequency vacuum tubes capable of operating at tens of gigahertz. They were used for amplification, radar, and even satellite communications. But vacuum tubes heat up, have a short lifespan, require high filament currents, and need high anode voltages. And some vacuum tubes are even sensitive to how they're installed. Scientists have always been searching for solutions, something better, and the Gunn diode became one of them. Any promising discovery or invention is first studied by the military. In this regard, the Gunn diode was a very interesting component. We remember that it was the 1960s, the height of the confrontation between the two superpowers during the historical period known as the Cold War. Missile interception and early warning systems, radar, various types of radars, and the latest forms of communication were top priorities. In 1962, American physicist of British origin, John Gunn, who was working at the time, at IBM, he conducted experiments with a homogeneous gallium arsenide crystal and discovered an interesting effect: the emergence of microwave oscillations. Later, this very effect became the basis for a diode that would eventually bear his name, his diode, the discoverer. Later, the Gunn effect was also found in indium phosphide crystals, gallium phosphide, and other semiconductors. Mainly, the Gunn diode was used in radar systems for radio location, in microwave transmitters, motion sensors, and so on. It was compact, energy efficient, and low maintenance, making it the ideal solution at the time. The main advantage of the Gunn diode was its low cost. At that time, it was one of the cheapest sources of microwaves. Of course, it's not as relevant now as it used to be, but it is still used in some areas. One of the drawbacks of gun generators is their relatively low power, which rarely exceeds a few watts in generator mode. Often, the power is in the range of tens or hundreds of milliwatts. But how does this diode actually work? Let's figure it out. The construction of the Gunn diode is quite simple. Usually, these diodes use a homogeneous crystal of N-type gallium arsenide. No barriers at all. As I mentioned earlier, it doesn't rectify anything and doesn't have unidirectional conductivity like a classic diode. The crystal consists of three N-type regions. There are two heavily doped N regions at the edges of the crystal and a thin, less doped active N region in the middle. A necessary condition for the effect to occur is reaching a threshold value of electric field strength of the field. Usually this is about 3 kilovolts per centimeter. Imagine a highway where electrons move without delays or anomalies. As the voltage increases, the speed of the electrons increases, which makes sense, but this only continues up to a certain threshold. When the field strength becomes too high, in the active region, the electrons sort of start to heat up, and some of them move into other energy valleys of the conduction band, where their effective mass is greater and their mobility is lower. To put it as simply as possible, the electrons become heavier and slower. Because of the drop in mobility, the field distribution becomes unstable, and a local region of increased electric field spontaneously forms. This is called an electric domain, or simply a domain. It's important to emphasize that this isn't related to the characteristics of a p-n junction. There simply isn't one here, and it's not the usual thermal heating of the crystal. This is an effect of electron heating and intervalley electron transfer. In other words, a kind of bottleneck appears in the form of the electric domain. Over time, more and more electrons accumulate in the domain, and they all become heavy and slow. In this region, conductivity worsens and the voltage drop increases sharply. Under the influence of the field, this entire bottleneck slowly starts to move from the active region toward the anode. Meanwhile, along the rest of the main path, electrons continue to move without obstacles, just as before. When the domain reaches the anode, it breaks down and disappears. The resistance drops sharply, and as a result, the current through the diode increases abruptly. After the domain disappears, a new domain often appears at the beginning of the main path, usually at the cathode, and the process repeats over and over again. As a result, at the output, we get a pulsating current or oscillation, all without any generator or external intervention. These processes, which are extremely fast, repeat tens or even hundreds of billions of times per second. This is what we call an ultra-high frequency oscillation. To put it as simply as possible, domains increase resistance and reduce current. Therefore, if we look at the current voltage characteristic of a Gunn diode, we'll see something familiar from our previous video about the tunnel diode, a region of negative differential resistance. But the reasons for the appearance of this region in the tunnel diode and in the Gunn diode are completely different. In the first case, the region forms due to the weakening of quantum tunneling, while in the second, it's caused by the formation of domains. In the case of the Gunn diode, as the external voltage increases, more and more of it drops across the domain, so the average current decreases. It is also important to emphasize that when operating in the classical domain mode, there is only one domain present at any given time. This, in simple terms, is the Gunn effect. But the question remains, why do domains form, and what is the nature of this phenomenon? Let's get to the bottom of it. The movement of the domains themselves is described by the classical laws of electrodynamics, and there is nothing unusual about that. But that's just a consequence, while the very nature of the effect once again leads us into the complex quantum world. I'll try to explain the nature of this phenomenon in simple terms. Imagine a car driving down a highway. Its speed gradually increases, and at some point, the car suddenly veers off and ends up on a parallel road, but instead of asphalt, it's sand. Naturally, it slows down sharply. Almost the same thing happens in a Gunn diode. On the physical level, the Gunn effect is based on three key phenomena. First, band theory. This is a quantum mechanical theory describing the movement of electrons in a solid. In materials like gallium arsenide, the conduction band is non-uniform. There are two main valleys or states in it where electrons can be found. It is this multi-valley structure of the conduction band that forms the basis of the Ridley-Watkins-Hilsum theory, which explains the physical nature of the Gunn effect. Then, the valley effect. According to this theory, there are two main valleys in the conduction band of gallium arsenide, the lower or central valley. Here, the electrons are light, have a low effective mass, and very high mobility, so they quickly carry electric current. The upper or side valley is higher in energy by about 0.3 electron volts. In this valley, electrons behave differently. Their effective mass increases sharply, and their mobility drops significantly. In band theory, effective mass isn't the amount of substance, but rather the curvature of the band. The smaller the curvature of the band in a given valley, the heavier the electron appears to the electric field. Second, electron heating. When we apply a small voltage to the diode, all the electrons are in the lower valley and behave normally. But as soon as the field strength reaches its peak, about 3 kilovolts per centimeter, the electrons gain more energy and essentially heat up. It's like adrenaline, but for electrons. This energy becomes enough for them to transition into the side valley through intervalley scattering. Third, negative differential resistance. At this moment, a paradox occurs. We increase the voltage, but the current drops because some of the fast electrons move into the slow and heavy side valley, causing instability in the crystal. A cluster of slow electrons forms, which moves toward the anode, disappears there, and then a new domain is born. These cycles create microwave oscillations. It is impossible without quantum phenomena. Energy valleys are a consequence of solving the Schrödinger equation for a crystal, and the concept of effective mass is a purely quantum result of the interaction between an electron and the periodic field of the lattice. That's probably all you need to know about the Gunn diode, but how do you make it work? Actually, to check if it works, it's enough to apply a certain voltage to it with current limiting. The wires and connections create parasitic inductance, and will get at least some radiation, and you can detect this radiation using a detector diode that can operate at such frequencies. But if you want it to work properly and efficiently, and to be able to adjust the frequency, you'll need to build a power supply circuit and make an antenna. With Gunn diodes, a horn antenna was often used, which needs to be designed for a specific frequency. You can calculate a horn antenna using online tools, but what you make the horn out of depends on your resources. Here are a couple of antennas that are completely homemade. To be precise, I first calculated the dimensions based on the required frequency and desired gain, then made a 3D model, printed it on a printer, smoothed out all the layers left from FDM printing, and finally, in a galvanic bath, coated it with copper using a chemical process. Next, we install our diode into the antenna and get a ready-made source of microwave radiation. A Gunn diode is a microwave device. It's difficult to demonstrate the processes happening inside it or to measure its characteristics, since I don't have the equipment capable of operating at such frequencies. But I still need to show the diode in action. The Gunn diode generates a microwave carrier. We take an audio signal and modulate this carrier with it, meaning we change its parameters in sync with the audio signal. Next, the antenna transmits the signal, the receiver picks it up, the detector extracts the audio, and we amplify it, just like in regular radio communication, only at microwave frequencies. That's exactly why we needed a second horn for making the receiver. The receiver, which is also the detector, basically consists of just one component, a centimeter range detector diode made in the USSR. The useful signal from the detector is filtered, amplified, and sent to the loudspeaker. Initially, I wanted to broadcast regular music using this setup, but unfortunately certain circumstances came up because of what I need to do. For the transmitting part, I need a low-frequency power amplifier with specific criteria. This'll take some time. I want to publish the video today. This part is being filmed at the very, very end. But we do have a signal generator, and we can set different frequencies on it. In general, the work will continue. It's clear and obvious that you can broadcast audio this way, but honestly, there's nothing particularly surprising about that. Let me explain a bit about how everything is set up here. We have a laboratory power supply, and the first channel is used to power our transmitter. Here is the Gunn diode, and in this horn there is a detector diode, which acts as the receiver. Then, from the detector diode, the signal is taken, sent to a small Class D amplifier, and then to a regular loudspeaker. The Class D amplifier is powered from the second channel of the laboratory power supply. And here's the signal generator, which we'll use to supply certain frequencies. Let's start. It's gonna be a bit loud actually because I was too lazy to install a volume control here. I'm turning on the power amplifier. There's a bit of noise now. I'll bring the microphone closer in a moment so you'll hear everything clearly. And let's start. Our transmitter is going to be loud now. Let's take a moment to make sure that absolutely everything is working exactly as it should be. Now we turn on our generator. Here, the distance can actually be quite large. Alright, now I'm changing the frequencies. Here's 20 hertz, 30 hertz, 40 hertz, 60 hertz, 70 hertz, 80 hertz, 90 hertz, and 100 hertz. Let's lower the frequency. Let's set it to exactly 1 hertz. There, that. It all done. It's working perfectly. A certain condition is required for the Gunn diode to operate. It needs to be supplied with a certain operating voltage, which is also called the bias voltage, usually from 5 to 10 volts. The value depends on the length of the semiconductor crystal. At the same time, Gunn domains are formed inside the diode. Negative differential resistance appears, and the diode becomes an active microwave element. The operating frequency of such a generator is determined by the electromagnetic resonance of the structure in which the diode is placed. And the physical frequency capabilities depend on the length of the diode's crystal itself. In this antenna design, the frequency is set by the distance between the diode and the rear reflecting wall. That is, by the electrical lengths of the resonate cavity. To tune the frequency in resonator designs, a special metal plunger is used, which also serves as the reflecting wall. Moving it changes the distance between the diode and the wall. As a result, it changes the resonant frequency. The smaller the distance from the wall, the higher the frequency. In addition to mechanical methods, there are other ways to change the frequency. From this, we can conclude that the Gunn diode itself does not set a strictly defined generation frequency. The frequency is determined by the external resonator. However, the maximum possible frequency is limited by the length of the active region of the diode's crystal itself. The shorter it is, the faster the domain reaches the anode and the higher the maximum generation frequency. Is the Gunn diode used in the modern world? Yes. And it's not about nostalgia for old military technology, but a consequence of fundamental physics. The Gunn diode is not an amplifying element like a transistor, but a bulk self-oscillator operating on the electron transfer effect. Oscillations in it do not arise due to external feedback in the circuit, but due to the moving electric field domain inside the crystal. This fundamentally distinguishes it from a transistor. So, where are Gunn diodes used in today's world? Gunn diodes are still used in areas where transistor-based oscillators are physically inferior or their implementation is impractical, for a number of reasons. Millimeter wave radars from 35 to 110 GHz, locators at 94 to 140 GHz, spectroscopy and gas analysis, laboratory microwave metrology sources, calibration generators, certain military satellite radar systems, motion and presence sensors. In some measuring instruments, a Gunn diode is used as a reference microwave generator because it provides a sufficiently clean spectrum. Gunn generators are still used in the millimeter wave range. The frequency of a Gunn diode is determined not by the circuit, but by the transit time of the domain through the active region of the crystal. This ensures a sufficiently clean spectrum and low phase noise in the range up to tens and hundreds of gigahertz. At very high frequencies, transistor efficiency drops sharply, gain decreases, parasitic capacitances dominate, and gate charge and discharge losses increase. The Gunn diode directly converts the energy of electron drift into an electromagnetic wave. The fundamental difference is that a transistor is a controlled electronic valve, while a Gunn diode is a moving domain of an electric field. It is the fields inside the crystal that create the oscillations. Again, it's important to note that this doesn't mean Gunn diodes are irreplaceable. It's just that in some devices where high power isn't needed and simplicity, reliability, and low cost are important, the Gunn diode is quite appropriate. Well, I hope after watching this video your head doesn't hurt too much and you enjoyed it. If you liked the video, let me remind you that the best way to support the creator and help make more videos like this is with a kind word or constructive criticism in a comments, and also a like. That way I'll know how interested you are in science popular videos. That's all for me for now. As always, this was Cassiana Cat with you. See you next time. Bye.